Hi, I'm Tim Dr. T. Shamillard, and I'll be your instructor for this course. I'm an associate professor in the computer science department at the University of Colorado at Colorado Springs, where I teach a variety of game design and development courses, and I teach some computer science courses once in a while as well. I'm also the program director for our Bachelor of Innovation in Game Design and Development. I have 5.5 years of indie game development experience in a company called Peak Game Studios that I formed with my two sons, and now I do my indie game development in my one-man shop, Burning Teddy. This is a 4-week course, and the graded work consists of an automatically graded programming assignment each week, and each of those is worth 25% of your grade. I've also given you a number of exercises that aren't worth any points, but provide you good practice as you engage with the course material. And I've also given you some optional Unity projects that also are not worth points, but provide you really good practice engaging with both C# and Unity game development. In week 1 of the course, we'll have the Getting Started lesson, which is what you're doing now. And then we'll look at abstraction, which is all about deciding which details matter and which details don't. And then we'll work on designing and implementing a console app class. In week 2, we'll take a closer look at methods and how they work. And in week 3, we'll work on designing and implementing a Unity class. In the final week of the course, we'll look at strings and Unity text. And we'll also figure out how to add Unity audio to our games, and then we'll have a finishing up lecture for you to watch at the end of the course. I wrote a book that we use in the first 2 C# programming and Unity courses at UCCS, and I've given you a free copy of that book in a week 1 reading. Thank you for taking this course. We'll use material from that book in all 4 courses in the specialization. This course continues to build on the foundation you've built in the previous 2 courses in the specialization, and it's based on the final third of our first C# programming for Unity game development here at UCCS. If you run into trouble with the course material, you can always post to the forums on the course, and of course you can also go to the internet for help as well. And finally, just like in the previous courses, I've provided a course topic index where you can click on a link and go to that particular topic in the appropriate place in the appropriate video to remind yourself about that particular topic. Let's go get to work. What will you learn about in this lesson? You'll learn what abstraction is, and people talk about abstraction in 2 different ways. They talk about abstraction, the process, which is the process of deciding which details matter as we try to solve a particular problem. And they talk about abstraction, the thing, the representation of the results of the abstraction process. And lots of people call an abstraction a model. That sounds pretty vague, I know. So over the course of the next few lectures, we'll actually get some practice so we can understand how abstraction works. Speaking of the next few lectures, we'll learn how abstraction helps us solve real-world problems, and we'll also learn how abstraction helps us solve programming problems. Recall from the previous lecture that abstraction is all about determining which details matter and which details don't when we're trying to solve a particular problem. In this lecture, we will get practice with abstraction by solving a problem. So, what's our problem? Our problem is that we want to implement a reservation system for a concert venue. That's where rock and roll comes from. And for this lecture, we will focus on the abstraction for a seat in that particular venue. What you should do at this point is you should pause the video and think about what details matter about a seat in that particular venue and what details don't for our reservation system. When you're ready, unpause the video and we'll talk about some of those details. Some of the details that do matter for a reservation system are the location of the seat, and that includes both the row you're in, which is often correlated with how far away from the stage you are, and the location in the row. So you may have a row that's further away, but you are more centered on the stage, so you prefer that instead. Certainly our reservation system will have to keep that information so that someone who's considering buying a ticket will be able to know where their seat will be in relation to the stage and use their own judgment to decide which pieces of location are more important to them. Another thing that matters to at least some people is the price of the seat. So we will have to keep track of in our reservation system how much it costs to sit in each seat for that particular concert. Because of course, better seats are more expensive, and so we need our reservation system to keep track of that information. Details that don't matter include how old the seat is, what color the seat is, what fabric the seat is, what materials the seat is made of, and all kinds of other stuff. They may be important to the designer of the concert venue. They may care about colors and so on, but somebody who's buying a seat for a particular concert probably doesn't care. To recap, in this lecture, we got some practice doing abstraction to determine what details matter and what details don't to solve a particular problem. In the previous lecture, we got practice with abstraction as we tried to figure out which details matter for a seat in a concert venue. This time, we will do a number of abstractions for a particular object, and we will see that the details that we decide matter are based on the problem we're trying to solve. So the big idea behind this lecture is that the details in our abstraction are directly related to the problem we're trying to solve. That means that there's no core truth about what the abstraction should be for a particular thing that we're trying to model. Remember, model is another word for the abstraction, the thing. And our example for this lecture will be a chair. Let's say our problem is that we want a chair to sit on. The details that matter for us, in this case, are structural integrity. We want to make sure that the chair won't break when we sit on it. And stability. We want a chair with two legs isn't very stable, so we want to make sure that whatever our chair is has appropriate stability. And those are the two details that matter if, in fact, we just want a chair to sit on. Let's say we want a chair that we're going to buy for our living room. So the details, of course, we still want structural integrity and stability. So if we're going to use the chair in our living room, but we also care about other things. We care about the style of the chair to make sure it matches the style of the rest of the furniture in our living room. At least my wife tells me that's an important thing. We care about the color to make sure we don't have clashing colors. We care about the fabric to make sure that it matches in some way or is a reasonable fabric or will wear well or something like that as people sit in it. And we probably care about cost. When I buy furniture, cost is an important consideration. So we probably care about that as well. So these details are different for purchasing a chair as furniture for the living room compared to just any old chair I can sit on. A third example is, what if we want to buy a chair as an investment? The details that matter in this case include the rarity of the chair, because chairs that are commonly available are not as good as investments as rare chairs. The condition of the chair, because chairs that are in good condition will be better in the long term as an investment compared to chairs that have been beaten up along the way. And cost, again. So if we spend a lot of money on a chair as an investment, it will take more growth in the value of the chair to increase our profit, rather than if we get a good deal on it. From an investment perspective, it's better to, here's a clue for you, buy low and sell high. That applies for chairs as well. So we do have cost here, and we had cost for the living room chair as well. And so we can have the same details in different abstractions, but the set of details as a whole is generally going to be different based on the problem we're trying to solve. To recap, in this lecture, we saw 3 different examples of doing an abstraction for a chair, and the details were different for each problem we're trying to solve. And to remind you, there is no core truth about a chair. There is no, this is the abstraction you should always use for a chair. The abstraction we use, the details that matter, depend always on the problem we're trying to solve. Last time, we learned that the abstraction we select is directly related to the problem we're trying to solve. In this lecture, we'll see how abstraction can help us in another way to focus on the details that matter. The example for this lecture is networks, and the problem is networks are incredibly complex, and we try to interact with networks in a variety of different ways. So different details matter depending on how we're trying to interact with the network. The solution to this problem is to model the network with different layers, typically 7 layers, and each of those layers contains different details based on the way people are trying to interact with that layer of the network. In essence, each of those layers in the network is an abstraction of the network. Let's go take a look at that 7-layer model of a network. As you can see, layer 1 is the lowest level of detail, so this is the physical layer. This is actually the physical medium, the wires that the bits are traveling across. How do we actually represent those bits, and so on. If we move up 1 layer to layer 2, we're looking at the data link layer, where we actually can do some error detection, where we can catch the fact that different packets have been corrupted in some way. We move up to layer 3, where we start worrying about how are we addressing these packets to make sure that they go to the right place. In other words, how should we route these packets through the network to get to their appropriate destination? And how do we flip the switches in the network to redirect packets different ways based on failures of particular nodes in the network and so on? The transport layer is the final layer contained in the transport service section. The bottom 4 layers are considered the transport service section. Layer 5 is the session layer, where we consider things like authentication, the user's identity as part of an internet session, if you will. In the presentation layer, layer 6, we think about encryption and compression and so on. And in layer 7, the application layer, we consider how do we actually display things appropriately so humans can actually interface with what's being provided to them. To recap, in this lecture we saw how we can take a very complex system like a network and build separate layers that contain different details based on how people would interact with that particular layer of the network, and each of those layers is really an abstraction in and of itself. In this lecture, we'll talk about how abstraction helps us when we code. The big idea is, when we write code, every detail we include in our abstraction or in our code costs us time and money during development, and potentially costs us CPU cycles and memory when we actually execute the code. Abstraction helps us because we can ignore unimportant details, saving those development and runtime costs. The implementation mechanism that we use for our abstractions in C# is the classes that we write. Let's take a look at a few examples. Our first example is using a vector 2D for location or velocity. The important details for this abstraction are the x and y components of the vector. For discussion, this is a really good abstraction for 2D or two-dimensional work, but it's a bad abstraction for 3D work because we haven't included the z component of a vector. For another example, let's talk about storing student information in a student object. We might store information like student number, the student's percentage in the course, and the student's letter grade. And this would be a useful abstraction if we're using it to calculate grades for students and record those grades. But it wouldn't be a good abstraction at all if we want to do demographic analysis about age and gender and how student performance relates to those demographic factors. For our final example, let's talk about storing GPS coordinates in a GPS coordinates class. The important details associated with that are latitude and longitude. And for the sake of discussion, that's a useful abstraction if we want to know our current location or if we want to get step-by-step instructions from a navigation app. But it's actually not useful if we wanted to do something like track altitude gain for a hike, because latitude and longitude does not include altitude data. To recap, in this lecture you learned that we use abstraction when we code to reduce the development and runtime costs of that code, and we also learned that, as we already know, the details that we pick for our abstraction are specific to the problem that we're trying to solve. An additional benefit of using abstraction is that our code is more readable because we haven't included details in our code that don't actually matter for the functionality we're trying to implement. The implementation mechanism for our abstractions in C# are the classes that we write, and a class can also be called the model of an object. What will you learn in this lesson? You'll learn how to design a console app class. You'll learn how to implement fields and properties. You'll learn how to implement constructors, and you'll learn how to implement methods. In this lecture, we'll design a console app class. Before we do, let's remind ourselves of the 3 important characteristics that every object has. Specifically, every object has state, behavior, and identity. The state of an object captures the current characteristics of that object. The behavior of an object tells what we can do to the object or tell the object to do to itself. And the identity of the object is so that we can tell one object from another in our game. And practically speaking, objects get their identity by the memory address that they live in. Okay, we're going to design a die class. The state of that die class will be the number of sides that the die has and what the current top side of the die is. We'll store the state in fields, but to support information hiding, we'll give consumers of the class access to the state through properties. For behavior, we'll provide one method, the roll method that lets the consumer of the class roll the die, so we'll have a method as well as our implementation of behavior. For identity, each die object will get its identity when we call the constructor to create a new die object, and that process is called instantiation. So this is a non-standard notation for showing a die class, but as you can see, that inner circle that has num sides and top side represents the fields that we have built in the innards of our class. So through information hiding, we won't let anyone actually directly access those fields. Instead, we will let consumers of the class access the state, the number of sides, and the top side through the properties, num sides, and top side so that we can control what they can do and what they can't do to those fields. Finally, to access the behavior, they can call the role method that has some internal processing that the consumer of the class doesn't know about, again through information hiding. So the state and behavior of a die object is exposed through the two properties and the one method. This is a more standard notation. This is unified modeling language, and this is a class diagram. So it's a diagram of our die class. Often you will see class diagrams with multiple classes in them, but for this particular lecture, we just have one class. And so our class diagram shows the name of the class, die, the fields that we're going to include, including their data types. It shows the properties we'll expose, including their data types, and it includes the method that we're going to expose, that role method. You can, if you choose to do so, include constructors in your class diagrams. I tend to not do that personally. That's why we don't have constructors in this class diagram, but you certainly can if you choose to do so. To recap, in this lecture, we designed a console app class, and objects of that class will have state, behavior, and identity. And I want to point out that this is just one abstraction of a die. This is sort of the standard use of a die, but if you wanted to use your die as a ranged weapon, for example, we would care about things like the mass and how easily we can throw it with our hands and so on. So different die abstractions apply based on the problem we're trying to solve. Our problem will be using a standard die. So this is a good abstraction for a standard use of a die. In this lecture, we'll implement the fields and properties of our die class. As a reminder, here in the UML diagram, I've put an orange square around the fields and properties we're going to implement, so let's go do that now. To start us off, I've created a new project called the die example, and this is the code we'll use to test our die class. We won't actually be able to do that until the next lecture, but I wanted to include it here now. And the first thing we need to do is add a new class for our die class. Because we've never done that before, I'm going to show you how to do it. On the right in the Solution Explorer, I can right-click my project name, die example here, the bold-faced die example, and I can say Add New Item. Luckily, the very top kind of item I can add is class, so I'll do that. But I'm going to change the name from class 1 to die instead. And when I click the add button, I get a new class named die. I'll add a documentation comment that just says this is a die. And for this lecture, we're going to add our fields and properties. The first thing I'm going to do is I'm going to create a region called fields, and I'll put end region as well for that region. And now I'll put my fields inside this region. We know we have two fields. We have num sides and top side, and we know they're both integers. And we declare fields just like we declare variables because fields are variables. They're just variables that are available throughout our class. Int num sides and int top side. As a reminder about regions, regions are not required for C#. Regions are a way for us to organize our code. They don't get turned into executable code when we build our solution or anything. They're just to help us organize our code, and we can collapse and expand our regions if our code gets really large and so on. So I regularly use regions in my code, but regions are really just a way for us to make it easier for us to work in our integrated development environment. Remember that we've talked about the fact that using information hiding is a really good thing in our object-oriented work. And we've said that our fields should not be accessible to consumers of the class, to code that's outside the class. We could actually make a field visible to consumers of the class by making that field public. And this keyword public is called an access modifier because it modifies access to this particular field. And this would be a horrible thing. We don't want to break information hiding by doing this, so we don't really want our fields to be public. We want our fields to be private. And because fields should be private, that's a best practice in object-oriented development. If we don't put an access modifier, the field is by default private. So we can just declare it as a variable. It will be private. It's good information hiding. So now we've declared our two fields for our die class. The next thing we'll do is declare our properties. I'll put those in a region as well. And we know we have two properties. Let's work on the first one first. Our first property is going to be for num size. And we do want to make our properties public because the whole point of doing our properties is to give consumers of the class access to the state of this die object. So in general, we'll make our properties public because they're for consumers of the class. We know that num size is an int. And I'm going to name my property num size with a capital N, just as we name our classes starting with a capital letter. And as we'll see later, we name our methods with a capital letter. That's standard C# capitalization. We actually have multiple ways that we can access properties. We can read those properties, we can write those properties, or we can both read and write. I'm going to show you doing both reading and writing for our num size property, but then we'll talk about why one of those is perfectly reasonable and one of those is totally unreasonable. Let's do read first. To provide read access to a property, we provide something called a get accessor. And this get accessor has red squigglies right now because I haven't finished implementing it, which I'll do momentarily. But the other accessor we can provide, as IntelliSense is showing us, is we can also provide a set accessor. So get accessors provide us with reading capability. We can get the value of the property, and set accessors provide us with write access. We can write the value of the property. For getting num size, we know that this property is giving a consumer of the class access to our state, access to the value of our num size field. So this right here will get the value of our num size variable. We know that's how variables work, right? We provide the name of the variable and the runtime system figures out the value of that variable. We're not quite done yet here because you can see we have red squigglies all over the place now. Just because we've retrieved the value of our num size variable, we actually haven't provided it to the consumer of the class that's trying to access this property. Programmers come up with weird names for lots of stuff sometimes, at least it seems like that until you're an experienced programmer. But this is one of those cases where we don't have a weird keywords to use. We're trying to return this value to the consumer of the class. So we say return num size. And as you can see, my red squigglies have gone away and a consumer of the class can now just read the num size property. And we've done that a lot in our coding that we've done as consumers of classes, but this is the other side. This is the implementation of the class. For a set accessor for num size, we want to set the value of our num size variable. And to do that, we assign it to a special keyword called value. And I know I've talked to you about this a little bit, so it's okay to have a review of how that works. When the consumer of the class accesses the set accessor for the numSize property, it's pretty common to use an assignment statement to say that the property is set equal to some value, let's say 5. Here inside the set accessor for the property, value gets the value 5, and then we set numSize equal to that value. So if you want to think of value inside a property as a special parameter that gets passed in when the set accessor is accessed by a consumer of the class, that's a reasonable way to think about it. Of course, set accessors can be much more powerful than this. One of the great benefits of using properties instead of making our fields public is we can control the validity of the data. Let's say we had a health field and a health property that had a set accessor. We know we want to keep our health between 0 and 100. So instead of saying something like health equal value here, we could say if health greater than or equal to 0 and health less than or equal to 100, then we set health equal to value. So if the provided value that gets passed in here is not in a valid range for health, we just don't change health. We don't let the consumer of the class destroy the validity of the data in our class. So there are some really powerful reasons to actually use set accessors with more complicated logic as appropriate to protect the validity of our data inside our class. Okay, one of these accessors is perfectly reasonable. The get accessor is perfectly reasonable. It makes sense to let a consumer of the class find out how many sides the die has. The set accessor for this property is totally unreasonable because what it would let the consumer of the class do after we created a die object is say, oh, I don't want the die to have that number of sides. If you think of this for a real die, it would be like picking up a die that you're using in a game and taking a file and shaving it off so you have another face on the die and then adding a number with magic marker on that face. That's called, wait, I know there's a word for it, cheating. So we are not going to provide a set accessor for our die. Once the die factory has created our new die object, you're not allowed to change how many sides the die has. So I'm going to delete that set accessor, and now I'll add the documentation comment that says gets the number of sides. The same arguments for get and set accessors apply for our other property, but this time we'll be getting the top side. So we'll call this property topside, and we'll return topside. And again, providing a set accessor for our topside is unreasonable. That would be like having somebody roll a die in a game, and if they didn't like the number that was on top, they could just reach over and spin the die and put a different number on top. That's also called cheating. And if you don't believe me, you should take a trip to Las Vegas and go to the craps table, and if you don't like your roll, just reach over and change what's on top of the die. You'll have an interesting life experience as you discover how the casino responds to that cheating that you're trying to do by changing the top side. So just as for numSides, we'll only provide a get accessor for our topside property. And I'll save all my changes and we'll build to show that everything builds fine. At this point, our next step should be that we actually test these properties, that we create a die object and we make sure these properties are returning the correct values for the die object we created. Unfortunately, we haven't written our die constructors yet, so we'll have to defer testing these properties until the next lecture. To recap, in this lecture you learned how to implement fields and properties in a class. You learned how we can control the visibility of our fields and properties by using access modifiers like public and private. And you also learned about how to implement and when to implement the get and set accessors for properties. In this lecture, we'll implement the constructor for a standard six-sided die, and in the next lecture, we'll implement a more general constructor that lets a consumer of the class specify how many sides the die will have. Although you can include constructors in your UML class diagrams, I tend to personally not do that, so let's go right to the code. Remember, our die class already has fields and properties. I'm going to add another region, and we know we're going to eventually have two constructors, so I'll call it constructors. Just as we made our properties public so consumers of the class could access those properties, we'll make our constructor public as well because we want consumers of the class to be able to call the constructor to create a new die object. The name of a constructor is always the name of the class. So I have to call my constructor die exactly this way with the same capitalization and everything. And then I put open and close parentheses, whether or not the constructor has parameters. We'll see in the next lecture a constructor that does have parameters, but this constructor doesn't. And I'll add a documentation comment. Constructor for six-sided die. Now you may not believe that a six-sided die is a standard die. You may think a D20 is the appropriate standard die, but most people, if you ask them about a die, they'll say it has six sides. So we'll make this constructor build a six-sided die, and in the following lecture, we'll add another constructor that lets the consumer of the class specify how many sides the die should have. Within our constructor, we need to initialize the state of our object and do any other work that we need to do, which doesn't apply in this particular case, to get our object ready to use. So a consumer of the class should assume, after they've called the constructor to create a new object, that object is ready to use. There shouldn't be anything else they have to do before they start using that object. That initialization is really easy here in our constructor. All we need to do is assign values to the num sides and top side fields. Num sides get set to 6 because we're constructing a six-sided die. And for top side, it really doesn't matter what we put here. This is like you just take a die and you place it on the table. At that point, it doesn't matter which number is on top. Somebody is going to roll the die before they actually use the top side in their game. So this is just creating the die object and conceptually setting it on the table. You will notice that even though we're programmers, we're not setting top side to 0 here. We'll actually number the sides of our die 1 through 6 rather than 0 through 5. Because dice are for humans to use, and even in a game that uses our die object, even if it's running on a computer, the dice should be labeled with faces starting with 1, not with 0. Now that we've built a constructor, we can actually test our code, both testing the constructor and testing the properties we wrote in the previous lecture. I've already added the code to do that testing. At the beginning, I've declared a new variable called standard die, and we've declared variables that are reference types before, that are objects. So we put the name of the class, which is the class we've been working on, and the name of the variable. And we know that for reference types, it's required that we create the new object before we actually start using it. So I'm calling the constructor that we just wrote using the new keyword, just like we always have done to create new objects in console apps. I've added a header that says the information that follows is for the standard die, because in the next lecture I'll be writing a constructor for the D20 die, and I want to separate the information I'm printing out for those two dies. And finally, I print out the number of sides for the die by accessing the numSides property for my standard die object, and then I print the top side by accessing the top side property for our standard die object. When I run my code, the results we get are exactly as expected. The number of sides is 6 because we set the numSides field to 6 in our constructor, and our numSides property retrieves the value of that variable or field and returns it to the consumer of the class. And topside is 1, also as we expected, based on the fact that we initialized our topside field to 1 in the constructor we just wrote. And that's all we needed to do to write our first constructor for our die class. To recap, in this lecture you learned how to implement a constructor, and you also learned that access modifiers apply to constructors. In this lecture, we'll implement the more general constructor that lets the consumer of the class specify how many sides the constructed die object will have. We'll add our second constructor here in our constructors region. And just like for the other constructor, we'll make this constructor public. And we'll call it die because constructors have to be the same as the class name. But unlike the previous constructor, in this one, we'll have a parameter. And we'll let the consumer of the class provide the number of sides they want the new die object to have. I'll add a documentation comment. Constructor for die with numSides sides. And for the parameter, we'll say it's the number of sides. Now you might have noticed that IntelliSense provided us a suggestion here, and I would have taken that suggestion, but I wanted to talk about why we need to take the suggestion that IntelliSense provided. Let's start by doing what feels intuitive. What feels intuitive is we want to set the field numSides equal to the parameter numSides that was just passed in. And as you can see, these green squigglies are actually telling us that we have a warning. And the warning says, assignment made to same variable. Did you mean to assign something else? And the answer to that question is yes, we meant to assign something else. This problem is caused by something called scope. So let's talk about scope. Scope tells us the visibility of a particular variable or parameter or field. So the scope of this field goes from the point at which this variable was declared to the end of the block in which this variable was declared. So this numSides variable is visible from here all the way to the closing curly brace for this open curly brace. So this variable is visible from here all the way down to here at the end of the class. And that's actually why we can do this in our numSides property, because our numSides field is visible here. In the constructor we're writing, we have a numSides parameter, which is visible between these curly braces, and this numSides parameter hides the numSides field because they have the same name. So what we need to do is we need to say, we mean the left-hand side of this assignment to be the field, and the right-hand side of the assignment to be the parameter. We don't actually have to do anything about the right-hand side because it's automatically the parameter, but on the left-hand side of the assignment, we need to say this numSides needs to be the field, not the parameter. The way we do this is with the this keyword followed by a dot. The this keyword is a self-reference. It refers to the object that I'm currently inside. And I know that's a counterintuitive idea for lots of beginning programmers. It's hard to wrap your head around that idea, but we've seen object references before. Anytime we call a method or access a property on an object, we put the name of the variable for the object, and then we put a dot, and then we put the property name or the method name or whatever. The same idea applies here. This is still a reference to an object. It's just a reference to the current object I'm inside. And when we use this syntax on the left-hand side of the assignment statement, it makes this be a reference to the numSize field, not the parameter. We'll go ahead and build. Over in my testing code, I've already added code for testing the D20 die, but I haven't commented out because it wouldn't compile until I wrote that constructor. Now it will, so I'll uncomment this code. And when I run, we get exactly the results we thought we should get, except I made a mistake because in my constructor, I also need to set topside. Let's try that again. And now we actually get the results we expect, where the D20 has 20 sides and the top side is set to 1. It's great news that this code works the way it should, but I find this structure unsatisfying because we have duplicated code. We have code here that sets numSides and topside, and we have code here that sets numSides and topside. And duplicated code in general is a really bad idea. We should be able to write our code in one place and use it in multiple places if we need to. And that's exactly what we're going to do here. We're actually going to reuse this constructor from this constructor. So I'm going to get rid of this code, and instead of including that code in the body of this constructor, I'm going to call the other constructor. The way I do that is I put a colon, and then I put, wait for it, the this keyword, and then I'm trying to call a constructor with one integer parameter. So I'll call a constructor with 6 because I want a 6-sided die. So the way the compiler works when it's checking my syntax is it says, is there a constructor that has one integer parameter? And the answer is yes, this one. So the code compiles fine. And when the code runs, if I call this constructor, what happens is it then calls this constructor. So it sets numSides to 6 and topside to 1. And we should test this code to make sure it still works fine. And it does. So the code behaves the way it did before I made this change, but I've refactored this code to be a much better structure because we don't have duplicated code. We just have the code that sets numSides and topside in one place, and we use this constructor both from the testing code directly for our second test case and indirectly from this constructor for our first test case when we were testing a standard 6-sided die. And that's all we need to do to add our second constructor to our die class. To recap, in this lecture you learned how to write a constructor with a parameter. You learned what the this keyword means and how to use it. And you learned how to avoid duplicate code by calling one constructor from another one. In this lecture, we'll implement the roll method for our die. Here's our UML diagram with the roll method circled with an orange rectangle, so let's go get to work. I'm going to add my method here in a new region for methods that I've added. The default for methods that we write if we don't include an access modifier is private, just like we get by default for fields. And that makes sense because we will have private methods for internal processing in our classes. Not in this particular class, but in general, we'll regularly have private methods as well as public methods. So if we want a method to be public, we need to add the public access modifier to it. And we do want our roll method to be public so that consumers of the class can actually roll the die object. The next thing we put is the return type for the method. And sometimes methods return something, like our takeTopCard method in our deck class returns a card object. But rolling the die does not return a value. It's just changing the internal state of the die. Specifically, it's changing the top side of the die. So we don't need to return anything from this method to the consumer of the class. We use a special keyword to say we're not returning anything, and that special keyword is void. The next thing we put is the method name. And then we put an open and close parenthesis, and if we have parameters for the method, we'd include them here just like we had a parameter for that second constructor we wrote, where the consumer of the class can say how many sides they want the die to have. But rolling the die doesn't require any information from the consumer that's calling this method. So we don't have any parameters for this method. And then we have the body of the method, where we actually do the work that the method is intended to do. I'm going to add my documentation comment that just says rolls the die. So what do we do in the body of this method? We need to pick a new top side for the die. That's what rolling the die does. It generates a new top side for the die. We may end up with the same top side because you can roll a 1 twice in a row, but we want to generate a new top side for the die. So we're going to modify the top side field, and we'll set it equal to something, and I can't set it to 1 like IntelliSense is suggesting because we'd always roll 1s then. What we really want to do is randomly pick a top side. I'm going to use the random class that's provided in C#, and I'll declare a variable that I'm going to call rand, and I'll take IntelliSense's suggestion. So now, after this line of code, I have a new random object. I happen to know that the random class has a next method, and in fact it has multiple versions of the next method. And I'm going to pick the one where I provide a min value and a max value. And the min value I'm going to provide will be 1 because that's the smallest number that I want for the random top side. I certainly don't want to put 6 here because the return value from next is going to be a number that's less than max value. So the min value is an inclusive value, but the max value is an exclusive value. I also don't want to put 7 because I might be using a D20. So this would work fine for a standard 6-sided die, but it won't work fine for a D20. Instead, what I want to put is num sides, but because the upper bound is exclusive, I want to add 1 to num sides. So now I'll get a random number that's between 1 and the number of sides that the die has. I've built our code to make sure we have no syntax errors there. Now let's roll each of our dice. So we roll the standard die by calling the roll method. On that standard die object, I'm going to want to print the top side and a blank line. And let's roll the D20 as well. And I want a blank line before I roll the D20. And when I run my code, we can see that the standard die had a top side of 1 and we rolled it and it has a top side of 1 again. And that's just how random numbers work. Just like we can flip a coin twice and get heads both times. We were unlucky there. We can see the D20 worked fine. I'll run it again so you can see that we actually can get a new top side for both kinds of dice as well. So at this point you're very happy. I've got everything working. This is fantastic. Unfortunately, in this manic depressive world of programming, I'm about to crush your hopes and dreams. We've actually done something dangerous in our code that is not good practice. To understand why it's not good practice, we need to understand how random number generation works in a computer. Here's how we generate pseudo-random numbers in a computer. And we'll talk about why they're not actually called random numbers before we're through. To generate pseudo-random numbers, we start with a seed. It's just a number. And typically that number is the current system time in the computer, though we can use a user-specified number as our seed as well if we want to for our random number generator. Then we take that seed as our starting point and we generate a sequence of numbers using some algorithm, some sequence of steps that say, here's the next number in our sequence of random numbers. They're not actually called random numbers because if we know the seed and if we know the algorithm, then we can perfectly predict what sequence of numbers will actually generate. Okay, given that understanding of how random number generation works in the computer, let's look at the documentation for the random class. One of the things that the documentation for the random class tells us is that initializing two random number generators in a tight loop or in rapid succession may cause trouble. We may end up with identical sequences of random numbers. And that's a problem for us because each time we call the roll method, we're creating a new random object, so we're calling those random number generators in rapid succession. And the reason that's an issue is because the random class is a pseudo-random number generator that uses an algorithm to produce that sequence of numbers, and it uses a seed as the starting point for that sequence. So if we call the random constructor very quickly in quick succession, those random number generator objects end up with the same seed, and because they use the same algorithm, they generate the same sequence of random numbers. How do we fix this in our code? In the die class, we shouldn't create our random object here because roll gets called multiple times in quick succession. And the documentation tells us, although I didn't show it to you, the documentation tells us that it's not best practice to create a new random object just for one random number. So the suggestion in the documentation is we don't do this here, that we do it here instead. And what this does is changes that local variable, that rand variable that we had inside the method that was only visible inside the method because of scope. We've changed that to be a field instead. And this field is accessible throughout the class, so it's still accessible within the roll method, but this random object gets created when the die object gets created. So we could actually initialize that rand object in our constructor down here as well, but it's also valid to just create the new object when we declare the field. So that's what I'm doing here. But that means we have only a single random object that will be used to generate all those random top sides for as long as this particular die object is around. And that's a better way, based on the random class documentation, for us to generate random top sides each time a consumer of the class calls the roll method. Because I've changed my code, I'll test it again, and it still works. And in fact, I will demonstrate by rolling each die multiple times. That we're usually getting a new top side each time, but as you can see here on the D20, that we got 7 twice in a row. And again, that's just how random number generators work. This time we got 3 4s in a row for our standard die. And finally, we got different top sides each time. We may or may not have seen that problematic behavior from using new random objects that we generated in quick succession, but it's definitely better to do it the way that the documentation suggested. We also observed that we can roll the same number multiple times in a row, even 3 times in a row in that middle run of the code that I did. And as a reminder, that's why, as game developers, we sometimes fake randomness rather than using pure randomness, or in the case of computers, pure pseudo-randomness. To recap, in this lecture you learned how to implement a method, you learned that access modifiers apply to methods, you learned about pseudo-random number generators, and even though we moved our random object from within our roll method to be a field in our die class, there's an even more robust solution that we should use when we actually develop games. What we should really do is we should have a game level random number generator. So any object that ever needs a random number gets that random number from our game level random number generator. And that's the most robust commercial quality solution to making sure we get a decent sequence of pseudo random numbers that isn't the same every time we run the game. As the last comment, we have now finished implementing our die class. What will you learn about in this lesson? You'll learn in more detail how method headers work. We'll explore more deeply how parameters work. You'll see what happens when we pass objects as parameters, and we'll refactor our nesting and boxes code to use methods. In this lecture, we'll learn how to write the method headers for and call the 4 different kinds of methods. And there are more than 4 different kinds of methods, but these are the 4 most common kinds of methods. So what does a method header tell us? It tells us who can call the method. It tells us whether we call the method on an object or a class. It tells us the return type for the method. It tells us the name of the method. And it tells us what information we pass into the method when we call it. Let's look at the syntax for a method header in a little more detail. Here's an explanation of the syntax for a method header. So this first piece, called the access modifier, tells us who can call the method. So if we make this method public, then anyone can call it. And if we make it private, then only other methods within this object can call it. And the square brackets mean that the access modifier is optional, and if we don't provide it, the default is private. The next piece of the method header tells whether we call the method on an object or on a class. And if we do not provide the keyword static, then we call the method on an object. But if we do include that static keyword, then it's on a class, not an object. And we've seen static methods before, so the console writeLine method is a static method because we call it on the console class, not on an instance of that class, not on an object. This tells us what data type the method returns. Then we provide the method name. And finally, we have a list of 0 or more parameters, pieces of information that get passed into the method. And for each parameter that we do include, we include the data type for that parameter and a parameter name, the way that we will refer to that parameter within the body of the method. So what are the 4 most common kinds of methods? There's a method that doesn't have a return value and doesn't have any parameters. There's a method that does have a return value and doesn't have any parameters. There's a method that doesn't have a return value but does have a parameter. And there's a method that has both a return value and a parameter. Let's take a look at those 4 common kinds of methods in more detail. We'll explore the 4 different kinds of methods in our deck class. And the first kind I mentioned was a method that doesn't have a return value and doesn't have any parameters. And our shuffle method is a good example of that. When we don't have a return value, we use this special keyword called void, and that says this method doesn't return anything. To specify that we don't have any parameters for this method, we just don't put anything between the parentheses in the method header. So we have our access modifier. We didn't put static because this is an instance method, a method that will be called on a specific deck object. We put our return type, and this is our special void return type that says we don't return anything. We put the method name. We put open parenthesis and close parenthesis, and as I said, 0 or more parameters, and in this case, 0 parameters. The reason that we have a void return type for shuffle is the shuffle method changes the internal state of the deck, it changes the order of the cards, but there's nothing that we have to give back to the consumer of the class that called this method. The shuffle method also doesn't have a parameter because it doesn't need any information from the consumer of the class. It can do its job without the consumer of the class providing any information. To call a method with no return value and no parameters, we put the name of the object, dot, the name of the method, and here between these parentheses you can see I didn't provide any arguments because this method doesn't have any parameters. The takeTopCard method in the deck class is a good example of a method that returns something but doesn't have any parameters. As you know, the takeTopCard method returns a card object. So if we're returning something from the method, we put the data type, the return type, that we're going to provide when we return something from the method. And the takeTopCard method returns a card object. We still don't have anything between the parentheses, so this method doesn't have any parameters because the takeTopCard method doesn't need any information from the consumer of the class to actually take and return the top card from the deck. So the takeTopCard method just takes the top card off the deck and removes it from the deck and then returns that top card to the consumer of the class. You'll notice that if the deck is empty, we actually return null because we can't take the top card from an empty deck, and we need to indicate somehow to the consumer of the class that called this method that there is no card to provide. The standard way to call a method that returns something is to put the name of the object in dot and the name of the method. This particular example doesn't have any parameters, so we don't provide any arguments here on the calling side, but we know after we call this method that we're holding a card object. And typically, we would take that card object and put it into a card variable so we can use it later, like to flip it over and to print the card and so on. It is possible, as I've demonstrated before, to call this method and not put it into a variable, and that's just taking the top card and throwing it on the floor. We wouldn't have a reference to that card object anymore if we do it that way, so we can't do anything with the card that we took off the top of the deck. The cut method in the deck class is an example of a method that doesn't return anything but does have a parameter, specifically the location at which we should cut the deck. Again, we have a return type of void to say that the method doesn't return anything because, like the shuffle method, all the cut method does is change the internal state of the deck. It changes the order of the cards in the deck by cutting the deck, but there's nothing to hand back to the consumer of the class that called this method. But the cut method does need information from the consumer of the class that called this method to know where to cut the deck. One way you can think about this parameter is that this parameter is like a local variable that we can use in the body of the method. So we can use location, and you can see I've used it in multiple places here in the body of the method to actually have the method do its job. The typical way to call a method with no return value but with one or more parameters is to put the object name dot and the method name But this time, instead of leaving this part blank between the parentheses, we provide an argument that gets passed into the method, and the parameter gets assigned the value of this argument. And we'll explore that in a little more detail in the next lecture. In case you didn't realize it, this call to cutting the deck is cutting the deck exactly in the middle of the deck. Finally, I added a method to the deck class called takeCard that returns something, a card, and has a parameter, the location of the card we want to take. And this method isn't a typical use of a deck. This is good for magic tricks, right? Pick a card, any card. But in general, when we use a deck, especially if we just deal from the top of the deck, we don't let consumers of the class just pick a card and take it from the middle of the deck or the bottom of the deck, because usually that's considered cheating. But I wanted to use this as an example to show a method that has a return type and a parameter. So the takeCard method returns a card object, and it has a parameter that tells which card we should take from the deck. To call a method with a return value and a parameter, I have the object name dot method name. I put whatever arguments the method expects here between the parentheses. And now that I'm holding a card object, I'm putting it into a variable because I want to do stuff to that card, like flip it over and print it. This particular example only has one parameter. I could also do something like float mass, so I can have multiple parameters. This makes no sense in the context of a card, but I wanted to show you that we can have multiple parameters. And here in the method header, if we have multiple parameters, we separate them by commas. And when we call a method with multiple parameters, we separate our arguments with commas. And you've seen that before when we call the version of the instantiate method in Unity that has us provide the prefab we want to instantiate and the world location and the rotation of that game object that we're instantiating. We separate those three arguments with commas. I'm going to get rid of this because I don't want to keep it. So now we've looked at examples of the 4 different kinds of method headers and how we call methods with those 4 different method headers. To recap, in this lecture we learned what information a method header provides. We learned how to write method headers for the 4 most common kinds of methods, and we learned how to call those 4 different kinds of methods as well. In this lecture, we'll take a closer look at how parameters work. And this can be a confusing area for beginning programmers, but it's really all about the information that the code that's calling the method passes into the method and how the method uses that information inside the method body. Let's go explore those ideas a little more. This is the same code that we had in the previous lecture, except that I've commented out some of the method calls on the deck object so that we can focus on parameters and how they work. And in the deck class, I've added this output in the takeCard method that simply outputs what the parameter value is inside this method each time we call the method. The first time we call the takeCard method, we provide an argument that's deck.count minus 1. And deck.count is 52 because we haven't removed any cards from our standard deck. So 52 minus 1 is 51. So the value of the argument is 51. If I run the code, you can see from that first line of output that inside the method, the parameter value is 51. And that's exactly as we would expect. So the argument gets evaluated here and we get its value, and then inside the method, location gets set to whatever value was provided for the argument. And then, as I said, we can use location here inside the method as though it's a local variable inside the method, so we can see the connection between the value of the argument and the value of the corresponding parameter inside the method. I want to point out for this argument, I could declare a variable called cut location and set it equal to deck.count -1 and add a semicolon and then pass in the value of the variable as the argument, and that works just as it did before. I could even put an integer literal here like 7 and run the code, and of course now the parameter value is 7, not 51. So the big idea is that the value of the argument gets evaluated before we actually enter the method. And we can use a literal, and we can use a variable, and we can use an expression like deck.count -1. And I'll put it back the way it was. So there are lots of ways that we provide those arguments, but they get evaluated, and then the location parameter gets set to whatever value the argument evaluated to. You'll notice that I took a card and flipped it over and printed it, and now I'm going to take another card, and this time I'm going to take a card from the bottom of the deck, which is typically considered cheating, but remember I added this take card method so we could explore this kind of method that has a return value and parameters. When I run the code again, we'll look at the third line of output, and you can see the second time that I called the take card method, when we got into the method, the value of the location parameter was set to 0. And this is actually one of the ways that methods are really powerful as reusable chunks of code, because we can call the same method providing different arguments, and that affects the behavior of the method. Specifically, it determines which card gets returned based on the value of the parameter, which is of course based on the value of the argument that we provided. So being able to call the same method with different information that we pass in, different arguments that control the behavior of the method, makes methods super powerful as reusable chunks of code. To recap, in this lecture you saw how a parameter gets the value of the corresponding argument on the calling side, and you also learned that it's helpful to think of parameters as local variables that we can use inside the body of our methods. At this point, we know how to pass data into methods using parameters, and we know how to return data from methods using a return type. This time, we'll write a method that gets valid user input. Here's our problem. Our problem is, whenever we need to get valid user input, we write a chunk of code that looks an awful lot like every other chunk of code we've ever written that gets valid user input. The solution to that problem is to write a method that gets valid user input. Let's go see how we can do that. Before we look at how to implement a method that gets valid user input for us, let's remind ourselves of what that pattern looks like from our iteration work. When we were talking about while loops, this is the code we wrote to get a valid health input from the user. We have a prompt for the information we want the user to enter, and then we read it in, and then we have a while loop that used a Boolean expression to make sure that the user input was between a lower bound and an upper bound. And while that was not true, while the user had provided invalid input, we printed out an error message, and then we prompted again and read in the value from the user again. So this was the pattern we used to get valid user input when we were getting health from the user. Now let's go see how we can do this with a method instead. Here's the method we'll use to get valid input from the user. And as you can see, I've called it getValidInput, and the return type is an int. And the return type is an int because this particular method will get a valid integer from the user. We could certainly write other methods that get a valid float or other data types that we need to get from the user. I will point out that I've included the static keyword here, and that's because I'm including this in a console app and I need the main method to call this method, and the main method is a static method, so that's why I have the static keyword there. The name of my method is getValidInput, and I have 4 parameters here, and these parameters map to the 4 different components of that pattern we saw to get valid user input. We have a string that we're going to use to prompt the user for their input, and I know we haven't talked about the string data type yet, but we've certainly used string literals all over the place in our code so far. We'll get to the string data type, but we can pass in strings as parameters, as we've seen all the way back from when we started using console.writeLine. So we have a prompt string and we have an error string, the string that we will print out when the user has provided invalid input. We have a lower bound that was 0 for health when we looked at our while loop example, and we have an upper bound that was 100 for health when we looked at our while loop example. So we need these 4 components to be able to get valid user input following the pattern we used in our while loops. I declare a variable to hold the user input, and then I print out the prompt string, and then I read in the user input into the value. Now I need to do my validation. So while the value is less than the lower bound, or the value is greater than the upper bound, and in our while loop example we were checking less than 0 or greater than 100, I print out the error string, I reprint the prompt, and I read in the new user input. This is really important because we need to make sure we modify value in the body of the loop, otherwise we'll end up with an infinite loop. Remember the ITM acronym for while loops. And then finally, when I get past the while loop, I know I have a valid value, and I can just return that value to the caller. Let's go to the main method and see why it's so useful to have this input validation as a separate method. Here in my main method, I'm going to have the user input a number of scores. And I don't know what that number is, so I'm going to put those scores into a list because we know lists can grow as we need them to, as we add elements to them. So first, I'm going to call this method to find out how many scores the user wants to enter. So my prompt string asks how many scores they want to enter. I need to provide an argument for my error string, and there's my error string. And because I'm going to limit the user to entering between 1 and 10 scores, my lower bound for valid input is 1, and my upper bound for valid input is 10. And remember, the getValidInput method returns an int, so we're going to save that int into a variable called numScores. So as we learned about how parameters work, these arguments get mapped to the prompt string, the error string, the lower bound, and the upper bound parameters in the method when we enter the method. The powerful thing about having this input validation as a method is now we can come down and actually get those scores from the user. And as you'd expect, we'll just do a for loop for numScores times, but here we're calling the getValidInput method again, but we're calling it with different arguments. We're calling it with a prompt string that says enter score, and I give the score number here, and because the user is a human, we don't want to ask them for score 0 the first time, we want to ask them for score 1. So I'm building a prompt string here that's different from the prompt string above. And I'm giving them a different error string because scores have a valid range of 0 to 100 inclusive, and I have a different lower bound and I have a different upper bound. So just as a reminder, one of the powerful things about methods is that we can change what the method does based on the arguments we pass in. The getValidInput method does the same general thing, it gets valid input, but we can change which prompt string and error string and lower bound and upper bound that method uses by passing in different arguments when we call the method. So we add our valid scores to the list of scores using getValidInput again with different arguments. And just to demonstrate this all works, I'll run the code and I'll enter some invalid inputs here first, and then I'll say I want to enter 3 scores. And for score 1, I'll show that it handles the invalid inputs there as well. And we'll say score 1 was a 100, score 2 is a 98, and score 3 is a 99, and everything works great. To recap, in this lecture, we wrote a useful method that we can use to get valid user input. In this lecture, we'll look at what happens when we have reference types, or objects, rather than value types as our method parameters. Our example for this lecture is cheating at cards. I've written a new card changer class that changes cards into aces. So I have a constructor for the class, and I have this public change card method that takes a card as a parameter and changes the rank of that card to be ace. I had to change the rank property of my card class to both get the rank of the card and set the rank of the card. You would never provide write access for a card's rank unless you wanted people to be able to change the rank of a card after that card was constructed. That's pretty atypical. It's generally considered cheating, but we're cheating throughout the example here, so we're providing this set accessor for the rank of a card. But you wouldn't actually do this in practice. In our main method, we build a hand of cards, and I'm not drawing these cards from a deck. I'm actually creating new cards to add to the hand. And again, that's not how you would typically do it, but I wanted to build a list of objects. And I wanted to have control over what those cards actually were. So this isn't a bad poker hand. It's 2 pair, 3s over 2s, but we could make this better by cheating. So my comment here says cheat, and the way we cheat is we create a new card changer object by calling the card changer constructor, and then we iterate over each card in our hand, and we call the change card method, passing in the current card that we're processing. Based on what we've learned about parameters and how they work, the card here inside the body of this method will be whatever card we're currently processing, but remember, card is a reference type. So we're actually passing in a reference to that card object, and we can change the state of that card object here in the body of our method. And it's actually changing the object in memory. That means that when we come back here, we can print our cheating results after we've changed all the cards to aces. We can iterate over the cards in the hand again and look at them by flipping them over and printing them. And I'll just run the code so you can see that we end up with a hand of 5 aces, which will look fairly suspicious to people who are used to a standard 52 card deck that only has 4 aces. But it demonstrates that we could actually change the state of each of those objects inside the method. And again, the big point is that because this is a reference type, we're getting a reference to a memory location, and so we can change the contents of that memory location. And because we change the contents of that memory location, those changes persist throughout the rest of our code because we actually changed memory. And it works that way because we passed an object as a parameter. To recap, in this lecture you saw how we can change the state of an object that's passed into a method, and that change persists after we return from the method because we actually changed data that's stored in memory. In this lecture, we'll solve a problem from our iteration work using methods. Our problem is we want to print out a box composed of asterisks using a user-specified width and height. The constraints on our problem are that both the width and height need to be between 3 and 20 inclusive, and a new constraint for this lecture is we need to use methods as much as possible. Let's go refactor our nesting and boxes code to do that. We're starting with the code that we wrote for our nesting and boxes lecture, but I added at the end the getValidInput method that we wrote a couple lectures ago. So we'll start by using that method to get a valid width and height. We'll start by replacing the getValidWidth code. So instead of all this code, we can just say int width equal getValidInput. And our prompt will be right here. And our error message is right here. And we know our lower bound is 3 and our upper bound is 20. So we'll get rid of this declaration of our width up above, and we can get rid of all this code. Let's go ahead and test this and make sure it works properly. And I'll try some invalid inputs. And as you can see, I got the error message incorrect, so let's just get out of here. And my error message is of course here instead. So let's try that again. And this is one of the reasons we test as we change our code to make sure it continues to work properly. Now that we know this works, I'll say getValidWidth and height. And we'll do the same thing for height. I'll get rid of this variable up here. I'll change this variable to height. I'll fix this to height. And I'll fix this as well. And boy, as I look at this error message should have been width, not height. So it's important, especially as you're copying and pasting stuff, to make sure that you're both copying the right stuff, and when you change it after you've pasted it, you need to make sure you change it properly as well. So finally, width should work fine. I'm asking for width. Width is in the error message, and I'm putting it into the width variable, and I'm asking for height and giving the height error message and putting it in the height variable. And I can now get rid of this code. So let's test this again, and I'll make sure I'm getting the correct width error message, and the error checking is of course working properly, and I'll ask for a 3x3 box. You'll notice that I didn't test again to make sure that height gave me the error message when I gave an invalid height. Once we know the method works, as long as we're passing in the appropriate arguments, we don't have to keep testing the functionality of the method. And that's one of the benefits of using methods, is once we've thoroughly tested those methods, we don't have to test them every time we call them. We just have to make sure that we're passing in the appropriate arguments when we call the method. So this is great. We are reusing that getValidInput method we wrote a couple lectures ago. Let's add another method that will do some of the stuff that we do a lot in this code. And if we look at this code, we can see that when we print the top row, we're repetitively printing an asterisk. And when we print the interior of the box, we're repetitively printing a space. And when we print the bottom row, we're repetitively printing an asterisk. So it seems like one of the ways that we could get a benefit from a method would be to write a method that prints a given character a certain number of times. So let's go ahead and do that. Down here after our getValidInput method, I'll add another method. It has to be static because I'm calling it from the static main method. This won't return anything because it's just going to print a character. So I'll say print character. And we'll need two parameters. We need the character we need to print. And we haven't talked in detail about the char data type, which holds a single character. We'll get there just as we'll get to strings very soon now. So this is just going to be a single character, and I'll call it character. And we need to provide how many times we want to print the character. And I'll call this parameter num times. I'll add the body of the method, and I'll add a documentation comment. Prints the given character num times the character to print and how many times to print it. And we actually already have code up in the main method that does this, so we can just grab this code and put it here and make two changes. First of all, we don't want to say I less than or equal to width. We want to say I less than or equal to num times. And we certainly don't want to print an asterisk. We want to print the character. Now for the for loop, if you've convinced yourself that you should always start I at 0, you can certainly write it this way instead. But you'll have to change this less than or equal to a less than instead. And this will iterate the same exact number of times as this will. So that's personal preference on your part. Let's go back up to the main method. And here, to print the top row, let's just say print character. And we know we're going to print an asterisk. And as we can see from the for loop we already have, we're going to print it width times. So let's get rid of this for loop. And we'll test our code. I won't do any more error checking here for the user input. So let's go a 3x5 box. And we can see that the top row printed properly. That's the change we made. Since we know this works fine, we'll take this code and we'll bring it down here to print the bottom row as well. And we'll test it. I went 5x3 instead of 3x5 that time. And you'll notice that I keep making a small change to my code and testing it, and making a small change to my code and testing it. And that's a really good way to approach both refactoring, which is what we're doing here. We're changing the structure of the code to make it higher quality code, but it's also a great idea in programming in general, because it's probable, not guaranteed, but probable, that if you run your code after making a change and you have a bug, and you didn't have a bug when you ran the code before you made the change, then it's likely, not guaranteed, but likely, that the bug is in the code that you just changed. Okay, we have another place here where we print a character repeatedly. It's in the interior of the box. So we'll call that method again. This time we'll print a space. And if I hide that box, you can see that we're actually printing this width minus 2 times. So I'll do that, and I can get rid of this for loop. I'll test my code again. I'll do a 5x3 box again, and everything is still working fine. Now we could stop there, but I want to write one more method. I want to write a method that prints the interior of the box, and I'll explain why I want to do that after we've done it. So I'm going to come down here and we'll add one more method. Again, it's void. It doesn't return anything to the caller of the method. I'll call this print box interior. And to do that, I'm going to need two pieces of information. I'm going to need the width of the box, and I'm going to need the height of the box. So I'll pass in width And I'll pass in height. And I'll add my body, and I'll add my documentation comment. Prints the interior of a box with the given width and height. So we have box width and we have box height. And I already have the code that does that. It's right here. So I'll just grab that code and bring it down here. And because my parameters are called width and height, and the code I just stole from the main method used width and height as well, I can compile just fine. And I'm very excited. I can go ahead and run my code and I say, give me a 5x3 box. And I only get the top and the bottom of the box. So just as a reminder, writing a method isn't sufficient. We actually need to call it to make the method run. So I'll say print box interior here, and I'll pass in width and height. And I'll run it one more time with another 5x3 box, and everything works great. I told you I'd explain why I wanted to do it this way when I decided to write this last method. And the reason I wanted to do that is because now our main method is really a description of the high-level processing that our whole program does. We get a valid width, we get a valid height, we print the top row of our box, we print the middle of our box, and we print the bottom row of our box. And that's nice. We can just look at this small main method and get an understanding of how the program works at a high level. And then we leave our individual methods to sort of do the heavy lifting of implementing the functionality of our program. To recap, in this lecture, we refactored our nesting in boxes code from our iteration work to come up with a more robust solution that uses methods. In the Unity classes lesson, you'll learn how to design a Unity class, how to implement the fields and properties in that class, how to implement the methods in that class, and how to use that class in a game. In this lecture, we'll design a Unity class. Specifically, we're going to design a fish class. And the fish class will be used as a ranged weapon, not a melee weapon, a ranged weapon. You could certainly build interesting games where fish are melee weapons, but we're going to use our fish as a ranged weapon. There are two important pieces of state that we need to include in our fish class. We need to include an explosion prefab that we can instantiate when the fish should explode, and we also should include the damage that is inflicted by the fish. For behavior, we want to be able to shoot the fish, and we also want to implement behavior when the fish collides with something else. For identity, the fish object will get created when the game object that the fish script is attached to is added to the scene. Here's the UML diagram for our fish class. As you can see, we have those two fields to hold damage and our prefab explosion. We have a damage property that has read access only. So if some other game object detects a collision with the fish, that other game object can access this property to find out how much damage the fish inflicted. And we have two methods, the fire method that will let us shoot the fish, and our onCollision enter 2D method that we can use to do whatever processing we should do inside the fish if the fish collides with some other game object. To recap, in this lecture we designed a Unity class, and this is just one abstraction for a fish. I'm going to use this fish in a shooting game, but if we were using a fish in a fish cooking game or a fish eating game or some other fish-related game, we'd probably want a different abstraction with different pieces of state and behavior for our fish class. In this lecture, we'll implement the fields and properties of our fish class. As a reminder, this is the piece of our design that we're going to implement in this lecture, so let's go write some code. This is our starting project. Almost all the stuff here is for the explosion that we're going to instantiate when we blow up our fish, but I've also included a fish sprite here as well. So let's drag the fish sprite over into the hierarchy window, and I'll rename it to be fish with a capital F. And of course, we're implementing a script, so I'll right click here and create a C# script, and this one will be called fish. And before I forget, I'll attach the fish script to the fish game object, and I'll open up the script. This is the default script template that I have set up, so I'll add a documentation comment that says this is a fish. I'll add a region for fields, and I'll add a region for properties. The first field that we'll add will be our prefab explosion, and we know our prefab explosion is a game object. But I want to be able to populate this prefab in the editor, so I need to mark this field as serialized field, and I'll save. And I know I often forget to populate my serialized fields in the editor, so we'll come back here into the editor and I'll select my fish and I'll drag my prefab explosion onto that field, because I know I often forget to do that. I'll save my scene and go back to Visual Studio. The other field that we need is for damage, and we'll make damage an int, and I'll call it damage as we designed the class. Now I could leave it just like this, and it turns out that in C#, a field that's of the int data type will be automatically initialized to 0, but that's not a good value for our damage variable, so I want to set it equal to something like 100. Let's say we hit a game object with a fish, and the game object has 100 health. When it takes 100 damage, we'll be destroying that other game object. So this is a one-shot kill fish, the way I've configured it here. You could certainly, as you integrate this fish into a game, you could decide that damage shouldn't be 100, it should be 50 or some other number, but for us, for now, we'll make damage be 100. The thing about fields is that they're visible throughout the class. So I can access this damage variable anywhere in the class. And that's good because the next thing we're going to do is implement our property. We want our property to be public. We know our property will return an int, and we called it damage with a capital D. And we said we're going to have a get accessor for this property. And IntelliSense is telling us exactly what we need, so we'll just take that, and I'll add a documentation comment that says gets the damage the fish inflicts. So I can now build my code and it builds fine. And back in the editor, nothing's really going to happen when I run the game, but I'll run the game anyway to show you that nothing happens when I run the game. And that's the implementation of our fields and property for our fish class. To recap, in this lecture we implemented the fields and properties of our fish class. And we also discussed the fact that we need to populate the serialized fields in our fish script once we've attached the script as a component to a game object in Unity. And this is different from console app classes, where we designed and implemented each class as sort of a standalone class. When we're designing and implementing Unity classes, we need to pay attention to the way that the script that we're attaching as a component to a game object needs to interact with that game object, both in the editor and, as we'll discover, as we actually include those Unity classes in games. In this lecture, we'll implement the methods in our fish class. As a reminder, here's the piece of the class diagram we're going to implement, so let's go write the code. The first method we'll implement is the fire method, but before we can do that, we should think about what that actually means. How should we actually fire the fish? And there's lots of different ways we could do this, but since I'm the person who's running this video, I've decided that we're going to click on the fish to make it go. So to shoot the fish, we'll click on the fish to make it go. Based on our previous work with the Unity game engine, we can imagine that we're going to add a force to a rigid body 2D to get the fish moving, but the question is, how do we know when to do that? It will help us to go look at the scripting reference. Here in the mono behavior class, we already know that there are a number of on-mouse something methods that are exposed by that class. We have on-mouse down and on-mouse enter and so on. And it turns out that there's an on-mouse up as button method that does exactly what we want. So this is called when the mouse is released over the same collider as it was pressed. So this is a click. We'll press the mouse button on the collider for the fish, and then we'll release the mouse button still on the collider for the fish, and that will shoot the fish. So you may feel some discomfort that we said in our design that we were going to implement a fire method, but instead we're going to implement the on-mouse up as button method. But this is a natural part of software development where we evolve our design as we discover more details as we try to do our low-level implementation. So we'll open up our fish script and we'll finally get rid of the start and update methods because we don't need those in our fish script. And I'll add a region for methods. And we know that we're going to implement the on-mouse up as button method. And as you can see, Visual Studio auto-completed that for us. We'll say fires the fish, because when the on-mouse up as button method gets called by the engine, we're going to fire the fish. As I mentioned, we already know we're going to add a force to a rigid body 2D to do that, but our fish game object doesn't have a rigid body 2D. So let's add one now. We'll select the fish game object. I'll add a component. It's a physics 2D component. And it's the rigid body 2D. I'm going to leave all of the default values as they are, but I am going to move this up because, as you know, I like my scripts at the very bottom. Okay, so now we have a rigid body 2D component attached to our fish. So the first thing I'll do is get a reference to the rigid body 2D component. And I'll accept all the suggestions, except I like to call this RB2D instead. And then we're going to add a force. So RB2D, and we're going to provide both a force vector and our force mode 2D. So for my force vector, we should think about the X and Y component of the force vector. And although it would be interesting to be able to aim our fish with the mouse before we shoot it or something, we're going to just shoot our fish straight up. And that means that the X component is 0, and the Y component needs to be non-zero, and in fact it needs to be positive to make the fish go up. This is a little bit of trial and error. We'll pick a number, and if the fish isn't moving fast enough, we could change that number. We'd probably wait to do that final tuning of the force vector until we've actually integrated the fish into a game. But for now, I'll pick 20. And for my force mode 2D, I'll pick impulse, as we've been doing, adding the semicolon as well. So we'll build over here, and we come back to the editor, and we play our game, and we click on the fish, and nothing happens. And we're sad. But if we think back to what the documentation said, It said the on mouse up as button method gets called when we've pressed down the mouse button and released the mouse button on the collider. And we don't have a collider yet for our fish, so let's add another component. And I can just use a box collider here. And again, I'll make it so my script is at the very bottom. So now let's try running our game again. And now when I click on the fish, you'll see he goes straight up. And that's exactly what we wanted. In case you didn't see that as well as you wanted to, I'll move the fish down a little bit. And I'll run the game again and click on my fish again. And as you can see, the fish moved up. So we've implemented the shooting the fish functionality that we had in our design, even though we implemented it using the on mouse up as button method. The other method that we said we were going to implement was the on collision enter 2D method, so that when the fish collides with something, we destroy the fish. So here in our methods region, I'll say void on collision enter 2D, and I'll just pick that by tabbing it, and it fills in the details for me. And I'll add a documentation comment that says destroy fish on collision. And this parameter is some collision information about the collision that we've just detected. We don't want to just destroy the fish, although we will want to do that. But we also want the fish to blow up. So we need to instantiate a game object. And it's the prefab explosion we want to instantiate. But we want to make sure that we instantiate the explosion at the location of the fish, not just at the default location of the prefab explosion, but we know how to get at the current location or position of the fish. That's transform.position. And finally, we won't rotate the explosion, even though that won't matter for an explosion. Okay. So I can build fine. Back in the editor, I have nothing for the fish to run into at this point, but I can solve that problem. I'll right-click the fish and I'll say duplicate. And this fish 1 I'll put at 0. And so when I play the game, I'll shoot this fish. And when it collides with this fish, both fish will detect the collision and both fish will blow up. Let's go ahead and test that. And just as I said, it works the way I said it would work. So we've implemented the behavior for both of the methods that we had in our original design for the fish class. And I want to point out that this is substantively different from developing console app classes. When we're developing our console app classes, we're just building standalone classes. But when we're developing our scripts for use in the Unity game engine, we have to pay attention to how our C# code interacts with functionality from the game engine. So as we saw, the on mouse up as button method, we had to make sure we had a collider attached to the fish so that method got called. We needed to make sure we had a rigid body attached to the fish so that we could add a force to it. So we have to pay much more attention when we're developing Unity classes to the interactions between the C# code we're writing and the functionality that comes in the Unity game engine. To recap, in this lecture we implemented the methods in our fish class. And as you saw, we decided not to implement the fire method we included in our original design. Instead, we decided to use the built-in mono behavior mouse up as button method. And that's a perfectly natural part of doing development. When we start dealing with the implementation details, it's perfectly reasonable for us to evolve our design as we discover more about our solution to the problem. This doesn't mean we screwed up the design or anything. This is just a natural part of software development. Of course, we also implemented our onCollisionEnter2D method, and now we've completely implemented our fish, so in the next lecture, we'll actually include our fish in a Unity game. In this lecture, the moment we've all been waiting for, we'll include our fish in an actual Unity game. So let's go do that now. Here's the game, and I'll play it first to show you how it works. I have a squadron of fish down along the bottom, and I have teddy bears that spawn from the top, and I can shoot the fish at the teddy bears to destroy the teddy bears. And if I miss, the fish actually gets destroyed and a new one gets put there at the bottom, and so on. And if I let a teddy bear fall all the way down, I get all kinds of explosions, and so on. I turned my fish into a prefab, and I also made the mass of the fish 1,000. I wanted my fish to be really massive. You may not have realized it when I was doing the fish development in isolation, but my game in the previous lectures didn't have any gravity. I did turn on gravity in this game though, because I need the spawned teddy bears to fall down the screen, and one good way to do that is to make them respond to gravity. That means that I needed to turn off gravity for my fish. And the way you can do that is by changing this gravity scale value to 0. So even though there's gravity in the game, our fish don't respond to gravity because I've scaled the gravity with a scale factor of 0, which means no gravity for the fish. I also added a teddy bear prefab that explodes when it collides with the fish. Let's go take a look at the changes to the fish script and some of the other scripts that I've included in this game. In the fish script, I didn't make any changes to my fields or properties. Firing the fish still works the same way. I did change the onCollisionEnter2D method to only explode on collision with a teddy bear. I know in the previous lecture when I implemented this method, I set it up so the fish exploded and was destroyed when it collided with anything, but in this particular game, I wanted to make it so it only explodes and is destroyed when it collides with the teddy bear. So I look at the collision info that gets passed into this method, and I see if the game object that I just collided with is a teddy bear is tagged with the teddy bear tag, and if it is, then I blow myself up. I also needed to add another method because I wanted to make it so when the fish left the top of the screen, it would actually be destroyed. So I had to add another method here. Once I put it into a game, I added another method that made it so when the fish became invisible, and the only way that happens is if it leaves the top of the screen, it gets destroyed. It doesn't blow up because it's off screen, so who cares, but we do destroy the game object. In our teddy bear script, I wanted to show you that in the onCollisionEnter2D method for the teddy bear, we check to see if we're colliding with a fish, and if we are, we get a reference to the fish script that's attached to the fish game object that we just collided with. So we know how to call the getComponent method to get a particular component on a game object, and I've saved the game object for the other game object that's participating in the collision into this variable, so I can get the fish component that's attached to that game object, and now I'm holding a reference to the script, and I needed that so I could access the damage property. And you should recall this is why we implemented a damage property, so the teddy bear reduces its health by the amount of damage inflicted by the fish. And the teddy bear also checks to see if it's died, if its health is less than or equal to 0. And if the teddy bear has died, then it also explodes and destroys itself. And I realized one other thing that I didn't mention about the fish. I said the method that fires the fish works the same way as it did before, but you'll notice that the y component of my force vector is much larger than the 20 that I used in the previous lecture. And that's because I made the mass of the fish so much more in my game that I needed to increase the amount of force I applied or added to the rigid body for the fish to get it moving at a reasonable speed. So that's another example of an interaction between our C# code and the Unity engine, specifically the mass of the game object that this script is attached to. We won't talk in detail about the fish squadron class that I implemented, but this is the class that makes sure we have a row of fish down on the bottom and that they get replaced when they disappear, which you probably noticed when I explode a fish when it runs into a teddy bear, the slot on the bottom row that corresponds to that fish gets filled with a new fish. So you should look at this at your leisure to see how I implemented the fish squadron. And that's what it looks like when we integrate our fish into an actual game. You should, of course, feel free to download the materials from this lecture so that you can both look at the code in more detail and perhaps even more importantly, you can play the game as much as you want, shooting teddy bears with fish. To recap, in this lecture we used our fish game object and the fish script that we wrote to attach to that game object in an actual Unity game. We discovered that we needed to evolve our design yet again by adding an onBecameInvisible method to our fish, and that's another reasonable evolution of our design that happens as we go through our implementation of game software. We also learned that if we change some characteristic of the game object, like its mass, we may need to change our code as well, like the impulse force that we apply to get the fish moving, and that's just another example of an interaction between the Unity game engine and the C# code that we're writing. What will you learn about in this lesson? You'll learn about the char data type. You'll learn about the string data type and some basic ideas behind strings. You'll learn how to apply a number of string operations, and you'll learn how to do text output in your Unity games. In this lecture, we'll explore a value type that we haven't looked at in detail yet. Specifically, we'll look at the data type we can use to store a single character. The data type is called char, although some people will call it char or car or something like that, but I'll call it char. And this value type uses 16 bits to store the value of that character. The single character we store is something called a Unicode character. Way back in the old days, we only used to use 8 bits for our characters because we were using something called ASCII. But it turns out it's a big wide world out there, and ASCII just wasn't big enough to store all the character sets we need to sort of have global reach for our characters. The operations for our characters, we'll discover those as we need them, but I will say that most commonly we're comparing a character or the value of a char variable to a character literal or another variable that also holds a char. Let's go take a look at how this works in code. Our example is from an exercise that you did in the selection module in the previous course, where you got a menu choice from the user and then you printed a message using an if statement. In that exercise, the menu choice you got was an integer because we hadn't learned about characters yet, but I've changed the menu choices so now the user enters a character to indicate their menu choice. So we print the menu, and then we prompt for a choice, this time prompting for a specific character. Then we have this complicated line of code to get their menu choice, and then we print out a message based on their menu choice. I'm going to comment out this line of code for the moment. and declare a choice variable and set it to a character literal. And you'll notice that character literals appear between single quotes. We've been using double quotes for string literals ever since we started printing stuff out using console writeline. So string literals appear between double quotes and character literals appear between single quotes. So if I were to run the code right now, you'll see that it creates a new game, and I didn't get to enter anything because I commented out the read line. But as I mentioned, one common thing we do with char variables is compare them to char literals. So here I'm comparing the value of the choice variable to the character literal capital N. And of course I could also compare it to the value of another variable that was also a char variable. Okay, let's get rid of that simple stuff I added, and I'll uncomment the more complicated stuff. And we sort of have a chicken and egg problem here. The processing I'm doing on the right-hand side of this assignment statement requires that we know something about strings, and we haven't talked about strings yet. We're going to do that starting in the next lecture, but I need to process strings to get at characters, and I need to know about characters to process strings, so just bear with me, and hopefully it will all be clear to you after we start talking about strings in the next lecture. For this line of code, I'm declaring a choice variable of the char data type, and on the right-hand side of this assignment statement, I start with the console.readline. And we've seen this before, and we know that the console readline method returns a string because we have parsed that string into an integer in some of the work we've done previously. So we know that after we call the console readline method, we're holding a string object. To simplify the Boolean expressions in my if and else ifs below, I want to convert the string that I got back to an uppercase string. Otherwise, I would need to write if choice equal capital N or choice equal lowercase n. And similarly for the other character literals that I need to check for the menu choices. So instead of doing that, I take this string and I call the toUpper method on it, and now I've made the string all capital letters, no matter what the user entered. But at this point, I'm holding a string, and I need to actually get at the first character in the string. And the way I do that is I can index into the string just as we've indexed into arrays and lists. And as we'll discover in the next lecture, a string is just a sequence of Unicode characters. So we know from our arrays and lists work that to get at the first element in the array or list or string, I use this square bracket notation and I put the index 0 between those square brackets. So this big chunk of code here on the right-hand side of the assignment statement gets a string, converts it to all uppercase characters, and then extracts the very first character in that sequence of characters in that string, and that's what we put into choice. So if I run my code now, I can enter a lowercase n, and it creates a new game for me. And I'll show you the rest of them as well, just so you can see that they work. And of course, they work fine if I enter a capital O, and I can quit the game. And I can even enter an invalid choice, and I get that's not a valid menu choice. And that's really all we need to know at this point about characters. The big ideas are that we put character literals between single quotes rather than between double quotes like we've been doing for string literals, and that we can declare char variables, and that we can compare the value of a char variable to a character literal. To recap, in this lecture you learned that we can use the char data type to store a single Unicode character. In this lecture, you'll learn about the very useful string data type. And a string is just a sequence of Unicode characters that char data type that we learned about last time, and string is a reference type, not a value type. So our strings are objects. Let's go take a look at some code that uses the string data type. We'll do a number of things to demonstrate the string basics in this code. I'll prompt for and read in a gamer tag. I'll prompt for and read in a high score. I'll extract the first character of the gamer tag, and I'll print out each of those values. So let's start by prompting for and reading in the gamer tag. We know how to prompt for things. We use console write, and I'll just say enter gamer tag. And we're going to store the gamer tag that the user enters into a variable. And that variable will be of type string. And I'll call it gamer tag. And we actually know from our past work that console.readline returns a string. In the past, we either parsed the string into a value type, like an int or a float, or, as we saw in the previous lecture, we did some processing on the string and then extracted the first character in the string. But here, we want the entire string. So we're going to take the string that's returned by the console readline method, and we're going to put it into our gamer tag variable. Let's come down here and print that value out. We might as well test this functionality before we move on to the next thing we're going to do. So I'll print out gamer tag, and I'll print out the value of that variable. And I'm going to want a space between the input and output portions of my code, so I've added a console write line there. As we've seen before when we did console write line, but I want to remind you, I can take a string literal and I can use plus to combine it with some other string. In the past, we've been combining it with numbers, for example, but the big idea is we can take two strings and we can combine them using plus, which is called concatenation. So we can concatenate two strings together, which is really just smashing them right next to each other to create a string that we use to pass in as an argument to the console write line method. So when I run the code, I'll enter my official gamer tag, and as you can see, it printed out the same gamer tag. So that's how we can just take the string returned by the console readline method and put it into a string variable. Next, we're going to prompt for and read in a high score. And you'll notice, by the way, that in my prompts, I'm not being polite at all. I am never saying please. It turns out that adding please to prompts in software really just give an extra word that users have to blast by as they try to figure out what you really want them to provide. So this is our excuse to not be polite. Don't put pleases into your prompts. They're unnecessary in software. We've seen this before. We're going to store the user input into a numeric data type, in this case an integer. So we need to parse the results of calling the console readline method into the appropriate data type. We know the console readline method returns a string, and then we parse it into an int and store that into our high score variable. We didn't really talk about this previously because we hadn't talked about strings yet, but you can't do a typecast. As we can see, the compiler error message tells us we can't convert type string to int. So we can't do a typecast. And we can't do a typecast because a string is a sequence of characters. So for each 16-bit chunk of the string, we have ones and zeros that are a Unicode representation of a character. Trying to typecast each of those 16-bit chunks of Unicode representations into the ones and zeros that actually represent an integer is not something that we can just automatically do. We have to do more work than that. and the more work that we have to do is int.parse. Now it's nice for us that somebody wrote the int parse method so we don't have to write it, but I'll tell you, you could write it. After we finish talking about extracting characters from the string, you could actually write a method that parses a string into an integer. All you'd have to do is walk the string and process each character and use an if statement to convert that character into a number. And then as you moved along the string, you'd of course have to multiply by 10 each time because you're moving through the places in the number. But you could absolutely write a method that does what the int parse method does, knowing what you know about loops and math and accessing specific characters in a string. We won't do that though. We'll just print out the high score. So my gamer tag again, and this time I have a high score, and as you can see, it prints out both of those values properly. The last thing we'll do is extract the first character of the gamer tag, which we actually saw in the previous lecture. We weren't extracting the first character of the gamer tag, we were extracting a menu choice, but the idea is the same. So first gamer tag character is equal to our gamer tag string. And of course we can't do this, right? Because gamertag is a sequence of characters and first gamertag character is a single character. So we're getting an error message that we can't implicitly convert type string to char. And we already know that, but we also know that we can index into our sequence of characters by using our square bracket notation, putting an index between those square brackets. So we'll print this out as well. And when I run the code, I'll make my gamertag ABC. I have a horrible high score. And as you can see, I've extracted the first gamertag character properly as well. So much of this we've seen before in our previous work, either recently in the previous lecture or in previous modules and or previous courses. But the big ideas are we can use console readline to get a string and put it right into a string variable. We can take the string returned by the console readline method and parse it into a value type. And we can extract a particular character from a string and put it into a char variable. And those are the foundational ideas behind strings. To recap, in this lecture you learned how to use the string data type. You learned that strings are a sequence of Unicode characters. You learned that strings are really useful for getting and processing user input. You learned that string is a reference type, not a value type in C#. And one more thing you should know. Strings are immutable. And immutable means once we create a string, we can't change it. We can't remove characters and we can't add characters. If we need to do that with a string, we actually use a different class called the string builder. But you should understand that if we're using the basic string data type, the string objects that we create are immutable. We can't change them once we create that string object. Last time, we learned about the string data type and some of the foundational ideas behind strings. And as a reminder, strings are sequences of characters. In this lecture, we'll learn some more interesting ways to extract information from strings. So what might we want to do with a string? We might want to convert a string to a value type, which is what we do whenever we parse the string. We might want to find a particular character in the string. We might want to extract a piece of a string and put it into a new string. And you may discover there are other things you need to do with strings. And if you do, you should read the string documentation to discover how to do those things. Let's go explore these ideas in a little more detail in code. The work we'll do in our code here is we'll read in a comma-separated value or CSV string. We'll find the location of the comma in that string. We'll extract the name and percent from our comma-separated value string, and we'll print the name and percent to make sure that we extracted them properly. We'll start by reading in the CSV string, so we'll need to prompt the user to enter a CSV string. And because we expect the user to provide their input in a specific format, we should tell the user what format they should use. So we'll tell them name, comma, percent. And now we'll read in their input, and we know how to do this. We'll have a string variable that I'll call CSV string. And we'll just do a console readline to put the user input into the CSV string. The next thing we need to do is find the comma location. And the way we would discover how to find the comma location is we'd open up the string documentation and we'd look for a method that would help us find the location of a specific character in the string. We'll look at the string documentation soon, but I already know the answer to this question. It's the index of method that we need to use. We know we're going to put the comma location into an int because the indexes of each character in the string are of course ints. So comma location will be an int. And as you can see, I can almost just accept what IntelliSense suggested, except I'm not going to do that. I'm going to just say look for the comma. Index of is an instance method. It's not a static method, so we use our CSV string variable and we call the index of method on it, and we provide the character that we're looking for. Just temporarily, let's print out comma location just to make sure we're finding the location properly. So I run my code and I'll say Bob, comma 0.1. And we get 3 as the comma location. And if that seems strange to you, remember we use zero-based indexing as we program. So the B character is at index 0, and O is at index 1, and B is at index 2. So the comma is at index 3. You might also wonder what the index of method returns if there is no comma. And it returns -1 if it can't find the comma. So theoretically, before we use this comma location, we should do some error checking to make sure that the user actually provided their input in the correct format. Because we're focusing on the string processing in this lecture, we'll just assume the user has provided their input in the correct format. Okay, so now we know where the comma is. How do we extract the name and percent? It turns out that we want to extract pieces of the string. Specifically, we want to extract the piece of the string that's before the comma for the name, and we want to extract the piece of the string after the comma for the percent. Now let's go take a look at the string documentation. And I'll tell you, I've already brought us to the appropriate place in the string documentation. We're looking at the substring method. There are actually 2 overloads for the substring method. For the first overload, we provide a single int. Int 32 in the documentation is the same as int, and the substring that we get back starts at a specified character position and continues to the end of the string. And that's not what we want to try to extract name. We don't want to go all the way to the end of the string. We want to start at the beginning of the string and only go the number of characters that are actually in the name. That means to extract the name, We need the second overload of the substring method where we provide two integer arguments. We provide the specified character position as the start of the substring, and we provide the length of the substring. Now you might think we should provide the ending character position of the substring we want, but it turns out that providing length is actually much more convenient for us, and we'll talk about why as soon as we go back to the code, which we're doing now. We know that the name will be a string, and we'll do substring, and in fact, IntelliSense suggested exactly what we should do. We want to start at the very first character in the string. That will be the B in our Bob, comma, whatever example. And the length of the substring we want to extract is actually comma location. And it works that way because we're using zero-based indexing. So the length of Bob is 3 characters, and comma location is 3, so we can just provide comma location here as the length of the substring we want to extract. And that works because we're using zero-based indexing. Let's print the name so we can make sure we're extracting the name properly. And I know I'll want a blank line. So I'll still do Bob, and Bob's getting marginally smarter, but we don't care, we're just extracting the name, and we extracted Bob correctly. The next thing we need to do is extract the percent. We know the percent will be a float, so we want to store the percent in a floating point value. It would be easier if we just stored the percent in a string as well, but that would be incorrect. We should store the percent as the data type that the percent really is. In this example, we're not going to do anything with percent, but we might decide that we wanted to add 10 to the percent. So everyone gets a letter grade boost in their percent, and to do that math, we'd have to store percent as a float. It's always best to store data in our programs as the data type that they truly are, rather than out of programming laziness trying to make it as easy as possible. We're going to use substring again, but we're going to use the other overload of substring where we start at a particular location and go to the end of the string, because the percent goes from just after the comma to the end of the string. And again, IntelliSense has suggested just what we need here. We don't want to start at comma location because then we'd include the comma in our percent. We need to start at comma location +1. Of course, we're getting a compilation error here. And our error is we can't implicitly convert type string to float. But we've seen this before and we know what to do. We know that this is a string and we know how to convert a string to a value type like a float. We'll use float.parse, and I'll hit enter so we can see the entire line of code here when I'm done. So we can parse this substring into a float and put it into our percent variable. And we've seen float.parse, we've seen int.parse, there's actually a bool.parse and a short.parse. There's lots of parses for converting strings into value types. We'll go ahead and confirm that we're extracting the percent properly as well. And Bob's getting really smart now. His percent will be 101.3%. And we've extracted the name properly, which we already knew. And we've extracted the percent properly as well. So this idea of being able to process a comma-separated value string is really useful to us. We can export CSV string data from lots of different spreadsheet programs, and then we could actually process that data here in our console apps or even our Unity games after we learn about file input and output, which will be in the next course in the specialization. But being able to take a string that's a comma-separated value string and extract the data from that string is really a useful skill to have. So knowing how to use the index of and substring methods to do that is really helpful. To recap, in this lecture we learned we can use a variety of string methods to do useful string processing. In this lecture, we'll talk about how to provide text output in our Unity games. And this is really useful if we want to share some textual information, like a score, with the player. Let's go take a look. We're starting with our fish shooter game that we developed previously, and I'm going to add a text display of the score to this game. There's a big idea associated with adding user interface or UI elements to our game. And the big idea is that those elements go onto something called a canvas. At least in our 2D games, you can actually add user interface elements in a 3D world if you wanted to do so, but in our 2D games, we'll put our UI elements onto a canvas. So I'm going to right-click here in the scene view, and I'm going to add a UI canvas down at the bottom. As you can see, when I added the canvas, I also got an event system, and we'll need that when the player is interacting with menu buttons or if they were providing text input as part of the game and so on. We won't actually use the event system in this game, but it comes automatically with our canvas and we'll just leave it alone. I'm going to rename my canvas to be HUD because this really is the HUD. And now I'm going to add a text element to our HUD. And I'll right click, and down in UI, I will pick Text Mesh Pro. And I'm going to just change the name of this right now to Score Text. And as you can see, we have text added to our screen. I'm going to do a number of things with this text. First, I'm going to anchor it to a particular location. And anchoring our elements to a particular location makes it so that they stay in that location even in the face of resolution changes, which is important to us. So I'm going to anchor this to the top middle, and then I'm going to move it up to be closer to the top. And I'm going to come down here to alignment, and I'm going to center my text. And at this point, I don't actually care what the text says because I'm going to handle changing the text in my HUD script, but I'll change it here to say score 0. It's also important, since I talked about resolution changes, that we come back to our canvas and look at the canvas scaler here in the inspector. And the default for our canvas scaler is that it's a constant pixel size. And that's a really bad idea if we're going to have different resolutions. So I'm going to change this to scale with screen size. And when I do, I need to provide a reference resolution. And I'll just say 1920 by 1080 is my reference resolution. Now that I've done that, you can see that my text is a little too close to the top and not quite big enough. So I'll come back to my text and I'll move it to be -100 instead. And I'll change the font size to be something bigger than 36, 48 for example. And I can change lots of characteristics of this text. I can make it bold, and you'll notice that it wrapped there. And I can avoid that wrapping by coming up here to the width of my text, and I can make it wider, and then I don't get that wrapping. So we can modify the width and height of our text component to make sure the text displays the way we want it to. And we can change the color and we can change alignment, as you've already seen me do. There's lots of stuff that we can do to change our text. But I like this the way it is for now, so we'll keep moving on. I do know that I'm going to need my HUD to be tagged. So I'm going to tag that now. It's obviously not one of the default tags, nor one of the custom tags that I already added to this game. So I'll add one more tag, and I'll call it HUD, and I'll save. And as you know, that doesn't tag it. I still need to come back and tag it with HUD. The other thing I need to do is take my HUD script and attach it to my HUD canvas. Let's go take a look at that HUD script now. Then we'll populate the serialized field that you can see in the inspector, and then we'll look at the rest of the code that actually uses the HUD script. So here in my HUD script, this is the serialized field that we're going to populate. And I've called the field score text, and here's the data type for the score text. It's TextMesh Pro UGUI. So TextMesh Pro Unity Graphical User Interface. I will say in the legacy text system, text used to be called text, but using TextMesh Pro, we have this other data type that we use for the text that we're going to display on a canvas. This class is found in the TM Pro or TextMesh Pro namespace, so we need to include a using directive for TextMesh Pro. I should have pointed out earlier, but I forgot because I already have TextMesh Pro installed in this project. TextMesh Pro comes in a separate package. So if you try to add a TextMesh Pro user interface element to your game and you don't have that package installed yet, you'll get a pop-up that looks like this pop-up right here, and you should just say that you want to import the TMP essentials. And that will install the package for you so you can actually use the TextMesh Pro user interface element. Okay, back to the code. So we have our text element here, and we've added the using directive we need to include that TextMesh Pro data type in our code. I also have an integer for the score, and I want an integer for the score so that we can do math. We can add to the score when we should. I also have a constant. That's a string. That's my score prefix. So when I display the score, I will display score colon space, and then I'll display the score. So let's see how we do that. Here in the start method, here's my reference to my TextMesh Pro UGUI object, and I can access the text property of that object. And if I access the set accessor for that property, then I can pass in a string. So I can pass in my score prefix, and then I can concatenate with score. But to make it concatenate with an integer, I need to call the toString method on that integer variable. And that makes this a string, so I can use plus to concatenate those two strings together and set the text property to that string. I will say that the TextMesh Pro documentation is not integrated with the Unity scripting reference. So if you want to find out about the TextMesh Pro classes, you should Google Unity TextMesh Pro documentation and follow the most promising hit, which will bring you to the TextMesh Pro documentation. Or you can just do something like this and scroll through all the possibilities looking for something that might work for you. That's probably worse than actually reading the documentation, because we've learned how important reading documentation is, but this is another option for you. Speaking of other options, there is a setText method right here that also lets us set the text And we can do some more complicated setting of the text by calling this method, but we're just going to access the property as you saw above. The only other thing we have in our HUD script is we have a public method that doesn't return anything. The method name is addPoints, and whoever's calling this method passes in the number of points to add to the score. And we do two things here. We add those points to the score, the integer field that we have in this script, and we set the text so that it includes the new score. So this updates the text display to display the new score. So who will actually call this addPoints method? The most reasonable object to call this method is the teddy bear, because the teddy bear will call that method when it gets destroyed so that we can add points to the game. I'm going to add a field to the teddy bear class, and all we really need as a field is a constant that says how much is a bear worth, and we'll make bears worth 10. When a teddy bear collides with a fish, as you know, we take damage. And here's where we should update the score in the HUD if in fact the teddy bear just died. The first thing we need is to get access to the HUD script so we can call the addPoints method. And this is why I added a tag to the HUD. So I want a reference to the HUD. And the way we'll get that reference is we'll call GameObject find GameObject with tag, and the tag we want to provide is HUD because that's how I tagged the HUD. And then I need to get the script component, the HUD script component that's actually attached to the HUD. So there's a lot going on here. We find the HUD game object, which is that canvas, which is a game object, and then we get the HUD script that's attached to that HUD canvas, and we put it into this variable. Now we can call the HUD addPoints method not with health, but with bear points. And since I now have two blocks of code here in this if statement, I'll say destroy teddy bear here as a comment. Okay, this builds just fine. So we'll come back to our game and run it, and immediately fail because we have this null reference exception. And if I double click it, we see that that's happening right here. And it's happening right here on this score text object because even though I claimed that I would populate this field when we came back, I lied about that. So let's actually populate the field like so, and we'll try running our game again. And this time we don't crash, and now I can shoot a teddy bear, and as you can see, my score went up. And that's how we can add text output to our Unity games. To recap, in this lecture we learned that we need to use a canvas to add our UI or user interface components to our 2D Unity game. And we also learned how to add and use a TextMesh Pro text component to convey information to the player. What will you learn about in the Unity audio lesson? You'll learn about the basics of how audio works in Unity so we can finally add sound effects to our game. And you'll also learn how adding an audio manager can support more complex audio behavior. In this lecture, we'll learn the basics of how audio works in our Unity games. So let's get to it. We're going to have a pretty simple game here where I will play a sound effect when the mouse enters the teddy bear. So my teddy bear game object has a box collider 2D attached to it so that we can detect when the mouse enters the collider for the teddy bear. And I also have a teddy bear script attached to the teddy bear, and that's the script that will actually play the sound when the mouse enters the collider. Before we look at the details, there are some big ideas behind the way audio works in Unity. The first big idea is we need an audio listener component attached to one of our game objects in the scene. And this is the component that actually hears the sound effects that are played by our game and then forwards them along to our headphones or speaker or whatever. So we need to make sure that one of our game objects has an audio listener attached. If I select our main camera in our scene, we can see that by default, the main camera has an audio listener component attached. So we know we get an audio listener attached by default to our main camera. We also need to have at least one audio source. So in this lecture, we'll attach an audio source to the teddy bear, and this audio source will play an audio clip, and then the audio listener will hear that audio clip and we'll hear it through our speakers or headphones or whatever. Now it turns out that we can have more than one audio source. We can have lots of objects with audio sources attached to them, and they can play their own sound effects whenever it's appropriate for them to do so. In our 2D games, it doesn't really matter where the audio listener is located or where the audio sources are located. In a 3D game, you can make a much more interesting audio soundscape where it matters where the sources and listener are, so you can sort of tell that something's behind you and those kinds of things. But we're not going to worry about it with this simple teddy bear game or any of the 2D games that we build in our courses. So we need to add an audio source to our teddy bear. I'll select the teddy bear object, and over in the inspector, I'll add a component, an audio component, and it will be an audio source. And I'll move this component up so my script is at the bottom. Now the way audio sources work is they play an audio clip. And as you can see with my first field here, I don't actually have an audio clip associated with this audio source yet. Over in the project window, I have an audio folder that I created, and I added a WAV file called OW to this audio folder. Unity supports a number of different sound file formats, but I tend to just use WAV files. So as usual, the way I populate the field is I just drag this OW audio clip over onto the audio clip for the audio source. And now the audio source has a clip that it can play when we tell it to play that clip. Now I haven't done anything in the script yet to actually play a sound effect, but listen to what happens when I start my game. As you heard, we actually got the OW sound played. And that's because my audio source component has the play on awake checkbox checked. And we don't want to play the sound effect when the scene loads. We only want to play the sound effect when the mouse enters the collider for the teddy bear. So I'll uncheck that box and I'll play the game again. And as you can see, it no longer plays that sound effect when the scene loads. Let's go add the code to the script to actually play the audio clip when the mouse enters the collider for the teddy bear. I know we're going to need a reference to the audio source component that's attached to the teddy bear because we're going to have the audio source play its clip each time the mouse enters the collider. And rather than getting that component every time we need to play that clip, we'll just get the component once and store it in a field. So I'll have an audio source field that I'll just call audio source. And then in the start method, I'll do our standard get component audio source, and now we'll get the audio source component that's attached to the teddy bear game object, and we'll store it in the audio source field. I've already included an onMouseEnter method that will get called on the first frame in which the mouse enters the collider for the teddy bear. But right now, we're not playing any sound when the mouse enters the collider, so at this point, we should go look at the audio source documentation to see how we can play the clip associated with the audio source. I just happen to have that documentation open, and if we scroll down and we look at the methods for the audio source, we can see, oh look, I just landed on it by mistake. We can see that there's a play method that we can call that plays the clip. And the clip is the audio clip that we populated in the inspector. As you can see in the documentation, there are lots of methods that we can call on the audio source to do lots of interesting things, but we're just doing some simple audio basics at this point, so all we need is the play method. So here in the onMouseEnter method, we'll just say the audio source should play the clip that's associated with the audio source. And everything builds fine. So back here in our game, each time the mouse enters the collider, we'll play that audio clip. And I won't talk as I do this so you can actually hear that audio.
Ow! Ow! Ow!
And there you go. Those are the basic ideas behind playing sound effects in your Unity games. To recap, in this lecture we learned that we need an audio listener to hear the sounds we play in our game. We learned that the main camera comes with an audio listener component attached to it by default. We learned how to import audio clips into our game. We learned how to add an audio source to a game object that we want to play sounds in our game. And we learned how, from within a script, we can have an audio source play its audio clip. In this lecture, we'll see how using an audio manager can support more complicated audio processing. For example, if we have game objects that we want to play a death sound when they're destroyed, we won't actually hear that death sound if we attach audio sources to those game objects, because when we destroy the game object, we also destroy the audio source that's attached to that game object. Using an audio manager can help us solve that problem. This lecture covers the audio processing portion of a Feed the Teddies game that we'll cover in much more detail in the next course. Let's go take a look. First, I'll play the game so you can hear all the cool sound effects, and then we'll take a look at how that actually all works. I won't talk while I'm playing the game so you can focus on the sound effects. And there you go. That's what the game sounds like when we play it. The core idea behind the approach for handling audio in this game is that we have a game audio source object that I added to the very first scene in the game, the main menu. And then we have some scripts over here for the audio processing. We have an audio clip name script. We have an audio manager that will handle playing all the audio. And we have a game audio source script that gets attached to this game audio source object, which you can see if I select it and come over and look in the inspector. All this game object has is a transform and that game audio source script. Let's go take a look at the code in those scripts. The audio clip name script is just an enumeration of all the different audio clips that we play as we play the game. For the game audio source, remember I said the game audio source is the audio source for the entire game. In the awake method, and awake is just called before start, I wanted to make sure that the awake method in the game audio source was executed before any of the other game objects in the scene executed their start methods. So Here in the awake method, I want to make sure that we only have one game audio source object in our entire game. And you might wonder how we could end up with multiple game audio sources, and the way that could happen is if we leave the main menu and then come back to the main menu, Unity is going to try to create another game audio source. So what we do is we check the audio manager and to see if it's not initialized. And we'll look at the initialized property soon. But if the audio manager hasn't been initialized, this is the first time we've tried to add a game audio source game object to a scene in our game. If that's the case, we add an audio source component to our game audio source. We call the initialize method in the audio manager, and this is a static method, and you can tell that because we put a class name here. And we pass in the audio source that we just added as a component to our game audio source, and then we call this method that we haven't seen before, called don't destroy on load. And what that does is it makes sure that the game object that this script is attached to, the game audio source game object, doesn't get destroyed as we move between scenes in the game. We want this game audio source to stick around for as long as we're playing the game. And those are the things we do if this is the first time that we've tried to add that game audio source game object to our game. If the audio manager has already been initialized, then this is a duplicate game object, so we're just going to destroy this one. We already have a game audio source game object in our game, so we don't need another one. Here in the audio manager, we have an initialized field that will keep track of whether the audio manager has been initialized, and we use this field so that we can expose that initialized property. We have an audio source that we'll use to play clips as necessary, and then we have a dictionary of audio clips. So we keep seeing these dictionaries all over the place in this particular game and in games in general. Dictionaries are really, really useful for us as we do our game development. This particular dictionary, our key is the audio clip name, and the value is the actual audio clip. So those are our fields in the audio manager. This initialized property just returns the value of the initialized field. When we call the initialize method, which we do from the game audio source script, if this is the first time we've added a game audio source game object to the game, we do a bunch of stuff here. We set initialize to true because we've now initialized our audio manager. We set our audio source field to the parameter that got passed in as an argument when we called this initialize method from the game audio source script. And then we load our dictionary. So for each of the audio clips in the game, we add an element to the dictionary with the key that's one of the audio clip names in that enumeration of audio clip names. And then we do this runtime loading of the resource that we've seen before. And this time we're loading an audio clip, and the audio clip's name is burger damage in this particular case. And it's keyed by the burger damage audio clip name. So we load all the audio clips into this audio clips dictionary. One of the great things about doing it this way is if someone decides later on to change the name of the burger damage wave file, the only place we need to change in our entire game is right here. We need to make this name match whatever name they changed it to. None of the other scripts in our game have to care that the file name changed. So this is a really good way to protect all the scripts from any ripple effects from file name changes. We just have to worry about it here in this one place. The last method we have in our audio manager is the method that actually plays a clip. So anyone who wants an audio clip played calls this method passing in the name of the audio clip that they want played. We look up the actual audio clip in the dictionary using the name that got passed in as the key. and then we take the audio source that we saved and we call the play one-shot method. I know I showed you in the previous lecture that we can call the play method to play an audio clip, but what I didn't tell you is that when we play an audio clip using the play method, the audio source can't play any other clips until that clip is done playing. And we don't want that behavior in this game. We want to be able to play overlapping clips whenever that's appropriate, so we need to use the play one-shot method instead. And this is sort of like a fire and forget method. When we call the play one-shot method, the audio source starts playing the clip we've provided, and then it's ready to play any other clip that we need to have it play. So this is the way to do it if we want to overlap our sound effects, which of course we want to do in our game. If I right-click play and say find all references, down here on the bottom you can see that there are 15 separate places within the rest of our code in our game that call this method to play sound effects. So we've consolidated all the work associated with playing sound effects in our game in the game audio source game object and in the audio manager script. And that's great because none of the other game objects in our game needs to have audio sources, and all they have to do to play sound effects is call the play method here in the audio manager. To recap, in this lecture we saw how we can implement a simple audio system using a game audio source and an audio manager. And in this implementation, we didn't need to have each game object have an audio source attached to it. This let us play sound effects for game objects where having the game objects themselves play those sound effects wouldn't have worked as well. Congratulations! You made it to the end of the third course in the specialization. Great job! If you completed this course and the previous two, you've completed the first C# and Unity programming course at UCCS. If you'd like to continue learning in a structured environment, there's one more course to go in the specialization. It's called Intermediate Object-Oriented Programming for Unity Games. But if you just want to call it quits now and go develop games, that's of course great as well. No matter what, thank you for taking this course. I really enjoy doing these courses on Coursera, and I'm really glad that you decided to join me in this course. Cheers.